can use those two design blocks to build up a larger block. In this case, what I want to do is create a 2-input multiplexer, which I'm going to call MUX2. Now, before we get onto this, I want to have a look at those two lines at the top. Library IEEE and use IEEE.stdlogic1164.all. I said that std logic, or standard logic, depending how you want to pronounce it, is the usual VHDL representation of a logic value. But that type is actually contained within a package called standard logic 1164. It's not defined within this file that we're writing here. We have to pull that definition out of the package in order to use it. And that's what these two lines here do. The first declares the existence of a library called IEEE. IEEE is a standard library that contains lots of useful stuff, which is automatically included with your tool, your simulator or your synthesis tool. In order to use the useful definitions from the library IEEE, we have a use clause. Use IEEE.stdlogic1164.all. And what that means is that we want to use all of the stuff that's in the std logic 1164 package. The idea of libraries will come back to us later when we are talking about configurations. But for now, let's move on to how we construct the entity MUX2 from the two blocks that we've already defined. Our entity MUX2 has three inputs: cell, which is a select line, and that controls which of the other two inputs, IP1 and IP2, are put out onto the single output, OP. Again, the entity just says what the interface to MUX2 looks like. It has nothing to do with how it works. How it works, in this case, is going to be defined by the architecture we've called struct, just meaning structure. Let's look inside this architecture. We have three instances of entities. The first one, which is called G1, is an instance of inv, the simpler of the two blocks that we've already seen. G3 is also an instance of inv, but it's a second copy if you like. So we have two invs inside our MUX2, and we also have an AOI, and we've called the instance of this G2. Notice that in order to instantiate these entities, to put them in place, we've had to say which architecture we want to use. So, for example, in G1, we've said we want to use the architecture A1, and we've also said what library we expect the entity to be found in. In this case, we're using the work library, and work just means the current working library. In other words, the same library that this file will be compiled into. So wherever MUX2 ends up, we're expecting that inv and AOI will be in the same library. Now there's more to it than just placing the blocks into the architecture of MUX2, because we also need to wire everything up. And here you'll see on the right how we do that. So our first instantiation, G1, maps A, that's a port on inv, to cell, the port on MUX2. And it maps the F output of this inv to the internal signal, cell B. Cell B isn't a port of MUX2, it's an internal signal inside the architecture, which is just going to be used to wire the sub-blocks together. This arrow here indicates the connection between the port on the left and the signal on the right. Now, in the way that we've done it here, we've specified explicitly what the entities are that we're placing inside MUX2. And while that makes it clear what's going on, it does tie us down rather. It means that inv, and indeed the architecture A1 of inv, have to be compiled before MUX2. They have to exist in the library before we instantiate them here. Now for a small design like this, that's no real penalty. But imagine you're working on a large system. If you're the system engineer looking at the top level, you may well want to test some of your logic before all of the subcomponents are actually ready to be used. How do you get around the fact that some of your subcomponents don't exist yet, but they have to be compiled? A way to get around this problem is that rather than directly instantiating an entity, we instantiate what's called a component. A component is a placeholder, a socket if you like, into which an entity will eventually be placed. By instantiating a component, we're saying there is going to be an instance of something which looks like this. It has this name, it has these ports, but we're not going to tell you which entity it really is yet. So in this example, we've declared two components, which we've given, in this case, the same names as our two entities, inv and AOI. And then we've instantiated the components instead of instantiating the entities themselves. So G1 is now an instance of the component inv. Notice that the architecture and library have gone away here. We're simply saying there exists an entity here and it has these ports, but we're not going to tell you which entity it really is yet or which architecture is going to be used to implement it. A component declaration is enough information for the compiler to be able to compile the file which contains mux2, because it can now type check all of the ports, which leads to this advantage here. Entities inv and AOI are not required to be library units before the analysis of mux2. Analysis is just the VHDL formal term for compilation. It can be inconvenient to have to declare your components every time you want to use them. These inv and AOI could be very useful and made use of many times throughout our design, and it's not very helpful to have to redeclare components as placeholders to place them in every single time in every single different entity where we want to use them. So we can put component declarations in a package. I mentioned packages earlier. StudLogic 1164 is a package, but you can create your own packages too, and that's what we've done here. We've created a package called myPackage, and then in that package created a component declaration for inv and another one for AOI. We've left out the details here just for simplicity. Now, in order to instantiate inv or AOI, the components, we don't have to declare the components over and over again. We can simply use everything in the myPackage package.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of Matt's webinar, everything you wanted to know about VHDL configurations, whenever you want, by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the KnowHow area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.